Big data is a sophisticated, scale-out compute environment with numerous functional elements and complex systems for the purpose of flowing data for analysis and automated decision-making. But let us take a deeper look by mapping out big data. We can first divide big data into two subdivisions: supercomputing and data analytics. Supercomputing is defined by the use of clustering, distributed data, and parallel processing to create compute systems able to complete massive jobs in relatively short periods of time. Data analytics is the construction of logical programming to analyze the data to derive value and deliver actionable results. Let us take a deeper look into both of these subdivisions. First, let's talk about the key concepts of supercomputing. You cannot have big data without supercomputing. The concepts of supercomputing need to be well understood for you to be effective in big data. So let's start with the first three core concepts: cluster, distributed file system, parallel processing. Clustering is the collection of multiple computers into a single computing system. Primarily, when we use the word clustering, we are talking about the infrastructure to create this compute system. Infrastructure such as racks, switches, and servers. Distributed data is discussing what happens within a cluster. The data is dispersed across multiple servers. In our supercomputing environment, we massively distribute data, and I mean massive volumes of data across huge numbers of servers. And then parallel processing. This is the use of multiple CPUs to execute different portions of a single compute job. Now, we are going to discuss parallel processing in some amount of depth in this course. All of us are well familiar with the concept that a laptop or a workstation will work on many jobs at the same time. But we need to think about this concept differently when it comes to parallel processing. We want to be able to take a single compute job and have it run at the same time on a large number of different servers. This is parallel processing, having a single job dividing its workload across many servers at the same time. Now, we will come back to this subject and spend a fair amount of time comparing the different types of parallel processing. We can well understand that the supercomputing subdivision of our big data map consists of three functional areas. They are Hadoop, NoSQL, and ETL. Let's talk about Hadoop for a second. Hadoop is an open source software which provides the backbone for our supercomputing platform. Hadoop has two key responsibilities. First, Hadoop is directly responsible for distributing and managing our large-scale volumes of data across the cluster. Second, Hadoop provides the software framework for creating and managing compute jobs in parallel across the clusters. Now, one of the most important aspects of Hadoop is it makes big data commercially viable because Hadoop is affordable at scale. NoSQL is a database purposely built to run on our supercomputing platform. It's called NoSQL, not because we don't use SQL commands, but due to the fact that we do not use relational database architecture. There are no tables made up of columns and rows as we understand it in a relational database when we look at NoSQL. The easiest definition to learn is NoSQL is a non-relational distributed store database. Let me say this again. NoSQL is a non-relational distributed store database. NoSQL databases provide the muscle for many of our big data solutions by storing large volumes of data while providing rapid access to the data elements. And finally, let me discuss extract, transform, and load. This last concept is moving data throughout our ecosystem, both into and out of the supercomputing environment, as well as within the system. A key requirement of our platform is to be able to access and manipulate data, lots of different data, and lots of different types of data. And to do this smoothly and efficiently, we must be proficient at ETL. It's a very important ongoing function in our supercomputing platform. This is a significant challenge for nearly all of our supercomputing platforms, and it requires a broad range of specialty skills. For example, the skill required for importing large video files is very different from the skill of extracting data from a relational database.